Welcome everyone to our first lesson of engineering mechanics. Statics, yeah, we'll be looking at the statics part of engineering mechanics. Today we are going to go through the basics of engineering mechanics. We are primarily going to focus on the equilibrium. We are going to focus on the equilibrium of rigid bodies. So this is the most basic things of engineering statics. So guys, let's go ahead and start. Equilibrium of a rigid body. First, let's start by defining what a rigid body is. Let's start by defining what a rigid body is. A rigid body, guys, it is just a body in which there are no deformations. So meaning if we apply forces to that body, it does not deform, it does not change shape, but realistically this does not happen. This is just an idealization that we are going to use for our analysis of rigid bodies. But you must not forget that nobody is perfectly non-deformable. They do deform to some degree, but the deformations are small such that we can ignore them. So yeah, that is the definition is there. It is a solid body in which deformations are zero or very small such that they can be neglected. So but what does it mean for a rigid body to be in equilibrium? What does that mean? All it means is that there is no net force acting on that body and there are no net moments or torques acting on that body. So the body is either moving at constant velocity and angular velocity, or stationary. That is it. There's nothing else besides that. For a body to be in equilibrium, it's either stationary or it is moving at a constant velocity or angular velocity. So guys, let me not go deep. Mathematically, all it means is that, if we are looking at, we'll be looking at two-dimensional problems as well as three-dimensional problems. So your Cartesian axis, we have the x, the y, and the z. So the sum of all the forces in the x-axis should be equal to 0. The sum of all the forces in the x-axis acting on the body should all sum up to 0, not forgetting to take into account their directions. Like we can say positive forces are forces that are acting along the positive direction of the x-axis, and the negative forces will act in the opposite direction. Yes, and also you can just do a vector summation, or this one is a scalar summation. I don't know why I put a vector symbol here. It's either you can use vector like those vector algebra, and yeah, as I've said, the sum of all the forces in the y direction should also equal to 0, as well as the sum of all the forces acting on the z axis. Remember, this is when we are looking at a 3D problem. We are doing an analysis of a 3D a solid, I mean a rigid body in 3D. And the last one is this one. This one, which states that the sum of all the moments, the vector sum of all the moments acting at a point on the rigid body should equal to 0. So for a body to be in equilibrium, it must satisfy all these four equations. This one and these three. It must satisfy these four equations for it to be in equilibrium. So let me show you what I was talking about. Let me take out a pen. Ooh, this is not straight. Okay. And we'll call this the x-axis and this the z-axis and this the y-axis. Let me draw my rigid body in space. This is my rigid body. So what we mean, let's say we have forces. Let me change the color. Like we have forces acting on this body. We have force 1. This is F1. And we have F2. Yes, F2. Yes, as well as let me draw a couple moment acting on the body, the body. Here's our couple moment, and here's another couple moment. This we call this one MA, and call this other one MB. So what we mean when we say a body is in equilibrium, the vector sum of these two forces, F1 and F2, should be 0. So now, hear me guys, I'm talking about a vector sum, not a scalar sum, because in order to use these equations, we'll need to break up these forces F1 and F2 into their components. F2, as you can see, it's a space force. It has a y component as well as an x component as well as a z component. All these forces are in space, even F1, but we'll assume F1 is parallel to the x-axis. Assume x1 is parallel to the x-axis. So yes, what we mean when we say that the sum of all the forces. Okay, let's start with this one, which is easier. This one. So let's choose any arbitrary point on the body. We'll choose this point. So if we take the moment sum about this point, we should get 0 if the body is in equilibrium. If we take a moment sum, this one and this one about this point, we should get 0. So here's what we mean. The body is in equilibrium, so the moment sum about point A, let's call this point point C should equal 0. The moment sum about point C should equal 0. We have MA plus MB. The vector sum of these two should equal 0 for the body to be in equilibrium. Do you understand, guys? And the vector sum of all the forces acting on the body. My pen today yes, that looks better. The vector sum of all the forces acting on this body should equal to 0, meaning F1 plus F2 should sum up. Their vector sum should equal to 0. You understand, guys? For the body to be in equilibrium. Yeah. So guys, that's the basics. So next time, on my next video, I'm going to introduce you to drawing a free body diagram. We're going to look into how you draw a free body diagram and show all the forces which act on a rigid body. And I'm also going to introduce you to support reactions. You know, engineering bodies are usually secured by some pins and joints. So those joints also, as the body is loaded, as the rigid body is loaded, those supports will also exert forces on the body itself to keep it in equilibrium. So we're going to look into how those support reactions work, like pins and rollers and all those sorts of things. We are going to be primarily looking at 2D problems as well as 3D problems. So guys, I'll see you next time. Thank you for watching. Please give this video a thumbs up and please subscribe.